Team Silver. We've got the pressure paint booth system. It is in an engine assembly plant in Dunlap, Tennessee. It's used to paint engine blocks. And we've got 3 booths here. For the experiments that we're doing in this class, we are going to have D1 and D2s closed. There's a little background on the system. Everybody's seen this before. We got a input motor power percentage. It goes through the system, and then the output is booth pressure in centimeters of water. Here's the basic procedure of how the system works. The operator inputs a particular percentage. It goes into the LabVIEW controller program, and then it is sent out to the equipment. And then once the equipment is run, inputs are sent back, or as the equipment is running, inputs are sent back to the controller, and then the data is output to an Excel spreadsheet. Here we have a steady state operating curve for our system. Pretty standard issue. Everybody's seen this a bunch of times. Our average was 35.2 centimeters of water. They 75% input. This is all 3 of our regions. Steady state operating curves. We had a little bit of error in the lower region at first. We had to go back and correct it a little bit, and got it somewhat close to linear. This is our step response model. Here we have a 10% step. But this is what we did a few weeks ago, and you can see our dead time and time constant and our gain for the system. These are the results we got for the step response. I tried to kind of condense them, put them all in one. We did step ups and step downs for the lower, middle, and upper areas. And you can see in the graphs here, these are our gains, dead times, and time constant results. This is our FOPDT model for the step response. This is used to represent the dynamic response of the system, and it allows you the ability to predict the output of a step up or step down. For this week, we're doing frequency response, and a few objectives are to observe time response of the output function of the pressure system, to the sine function, input at various frequencies, and then using Bode plots to compare. It's also used to observe the impact of different parameter values on the Bode plots, and to observe the sine responses of the approximate mathematical model for the system. Here is an example of a frequency response graph for our system here. Ran for 20 seconds. Again, you input your baseline power, and then your frequency, your amplitude, and your time. We ran about 10 trials. We actually ran a bunch more than that, but we ended up getting some kind of weird data, so we only used about 10 of them. And this is a diagram of how you get your various, you get your delta M, your delta C, your period, and your T are obtained. From that, you can get your amplitude ratio and also your phase angle. These are a few equations that we use to calculate those. AR stands for amplitude ratio. K is your gain. Tau is your first order time constant. And PA being your phase angle. This was a sample that we took from our data. You can see here that our gain was 1.9 centimeters of water per percent. Our FU being 2.4 hertz. As this crosses 180, take it straight up. Our 1 OK CU is 0.885. And here is some of our data put against the model that we had. You see our frequencies are from 0.1 to 2.4. These points here is the 1 over KCU. This is the gain of our system, and this was the gain of the model. And then here is the same data as a phase angle from 1 to 2.4 hertz, and then 180 being where the maximum. Okay, here's our frequency response for gain for our different sections of our system. You see it's a little bit, it's lower, and it increases as you go up in pressure. Our ultimate frequency is, we were having some trouble with this, but it's looks like it's a little bit higher in the middle there. And our time constant was a little bit skewed there too. Some of this data is a little bit last minute. This is our step response versus Bode plots. You can see this step response in Bode's for lower, middle, and upper, and time constant and the dead time as well. So in conclusion, frequency response is pretty useful for finding different frequencies of the systems, and used with steady state and gain, dead time, and time constant. Modeling for the frequency can be obtained. That's